Please take a moment to read over this slide. So please note that this webinar is sponsored by Provenance Consulting and reflects their views, opinions, and recommendations. Now, I would like to reintroduce our speaker, Justin Phillips. Justin is the Relief Systems line of service manager at Provenance Consulting and holds a BS in Chemical Engineering from Texas A&M University. He has more than 11 years of experience in the petrochemical industry. Welcome, Justin.
Thanks, Armani. All right, so before I really begin speaking, I want to go back over some of the slides that we saw as Armani was doing the introduction. One of the biggest benefits out of these webinars is, in my opinion, the Q&A section. So please, if you've got any questions that you want answered, please put them into the Q&A. If we don't get to them during this call, we will get them answered. We will make sure that the question is listed inside of our slide deck as well as the answer. There's a bit of a bonus at the end in the Q&A section. So my background is almost exclusively flare and relief systems, not so heavy on the PHA. However, we also have joining the call today and who will join in the Q&A session, Tony Powell, who is the PHA line of service manager for Provenance Consulting. So we too should be able to tag team any questions that we get. So I'm looking forward to the Q&A section. Quick overview of today's topic. The biggest idea and the thing that I want everybody to take away from this presentation is to get the most bang for your buck from your relief systems design and your PHA. Too often I see that PHA teams don't interface with relief systems teams and vice versa. Relief systems teams either don't interface with PHA teams or they don't take a look at PHA reports once they're finished. Both of these types of resources are very, very valuable, and I think that you can get a whole lot out of it. Save yourself some time, money, and save yourself from some hazards as well by recognizing how similar they are and how you can interface with them better. There's kind of three main parts to today's presentation. The first is to identify overlaps. So somebody with a PHA background maybe doesn't necessarily do a lot of relief systems work, and likewise, someone with a lot of relief systems background may not do a lot of PHA. There's a number of us in the industry who don't really specialize in either of those things. I'm sure that some of the people calling in today are working for a process engineering company. Maybe they do process design. Maybe there's others among us that are unit operations engineers or mechanical integrity experts. And so they themselves also don't necessarily participate in PHA or relief systems on a daily basis. So the first part is to identify for all parties, where do we overlap, where are we different. Following that, we'll talk about minding the gaps, understanding kind of the nuances when it comes to leveraging relief systems design inside of a PHA. And then the final part of this presentation, I'll provide some recommendations on how to boost that relief systems and PHA relationship. Briefly about me, just a quick slide. Armani already did a great introduction, so I'm not going to belabor it too much. And on to the first part of our presentation, identifying relief systems and PHA overlaps. So very, very basic refresher. I'm not going to go through complete definition of all the different types of PHAs that you can use because there's a myriad. You can use a HAZOP or a checklist or a what if, and then there's a couple of different sidebar types of evaluations that you can do as well. But the big idea behind a PHA is that a group of people with various backgrounds tends to get together. They look at causes, they look at consequences, and they look at the risk associated with that. So if you've got too much flow, what kind of consequence could that have inside of your system that you're looking at? What's the risk associated with it? And risk being a kind of a combination of likelihood and then severity. And if there's something that kind of bubbles up to the top as posing a hazard or a risk, we look at safeguards. What do we have in place that could prevent this? Is it instrumentation? Is it just a process nuisance? or are we going to have to use a PSV to defeat the scenario? Sometimes some companies, not all companies, will use something called a LOPA, a layer of protection analysis. But again, it really does depend on the company and whether or not they want to go there. Real quick on LOPA, just kind of a bit of a refresher on the LOPA end. Again, not all companies use LOPA, but some of them do. And then on top of that, every company is different. Some companies will have a different LOPA process than others. LOPAs can get triggered by different things, but in a very generic sense, you can kind of see in this risk matrix, which is also very generic. In this situation for company XYZ, anything that may cause a fatality or a permanent disability, anything that's really high up there on severity, maybe it triggers a LOPA. And what you do in a LOPA is you determine how many layers of protection you need in order to get yourself out of that scenario or to mitigate the risk effectively so that you are not faced with something so severe. Sometimes PSVs or pressure safety valves or PRDs, pressure relief devices, I may use those interchangeably, but I really do mean the same thing, are used to fill those gaps. But questions that you have to ask yourself, and it's usually very company specific, is, how many credits can I get for a relief device? It could depend on a number of factors. Is it clean service? And you could determine that by looking at inspection reports. Also, could you get more than one IPL credit for a PSV? Could I get duplicates of credit for multiple PSVs? It depends on the number of PSVs you have and whether or not you need one or two or three for a given scenario. But again, it all really just does depend on how a company treats its LOPAs. With Relief Systems workflow, there are some similarities with PHA. Steps 1 and 2 are really just basic data collection. That is, preparing to work. It's looking at the process safety information. It's reviewing the P&IDs. It's kind of getting everything ready to go. But then 3 and 4 are really where we start to see some similarities between PHA and Relief Systems. Inside of Relief Systems design, when you get to overpressure identification and rationalization, when you're looking for things that could go wrong and you're stating how those things could go wrong, that's very similar to the cause part of the process in PHA. Likewise, after a Relief Systems engineer identifies an overpressure scenario and provides the rationalization, the very next step is to do rate quantification. Like, what is the required relief rate going to be? And then after that, if there's a relief device present, performing sizing calculations on it for the relief device and pressure drop calculations as well. And the rate quantification and the device sizing is somewhat similar to a PHA in the consequence step and the safeguard step. Now, typically, PHAs won't be doing any calculations for PSVs, but a PHA might ensure that the scenario is addressed in the Relief Systems design documentation as a good practice. And then also just sanity checking on required relief rates. As far as personnel and resources, there is, you can think about it as a Venn diagram, as you can see on your screen. PHAs tend to be very people-focused. You can see that. That is one of the things that's different about PHA than Relief Systems design, is that it's lots of people sitting in a room coming up with scenarios, whereas Relief Systems is not so much of that. For Relief Systems, there's lots of calculations, lots of additional documentation that's reviewed versus a PHA, and that's really because of the nature of the work. PHAs tend to be very qualitative in nature, whereas Relief Systems, the final kind of deliverable from Relief Systems design, is very quantitative in nature. However, there is some overlap. So whereas a PHA may have a bunch of different people in the PHA, Relief Systems and PHA may both share Relief Systems experts. The other things that are common are reviewing process technology, having an understanding of what's going on inside of the process, understanding how instrumentation may function, understanding reactive hazards, understanding the heat material balance associated with the process, and then, of course, P&IDs. Both parties need to use P&IDs. There are different goals and outcomes for either. The success of a relief systems engineer or a relief systems team is to be both accurate and precise. They have got to be right on the money. They've got to make sure that the calculations are bulletproof and that the scenarios are well rationalized. Whereas a PHA team is not so much about precision, but it is about accuracy. The goal of the PHA team is to ensure that all scenarios are identified, basically that everything hits the target. It doesn't need to hit dead center, but that everything is identified and gets on the target. In other words, as the PHA team, you just never want to miss that target. With a relief systems team, you want to hit bullseye. Real quick recap on similarities and differences. Both groups, Relief Systems and PHA, focus on identifying the causes and consequences of process hazards. Relief Systems tends to focus specifically on overpressure scenarios, pressure excursions, but both parties do want to identify the cause of those and what happens because of those. Both of them require lots of engineering judgment and process safety information. However, the big difference is Relief Systems assumes that the worst case scenario can happen. PHA considers both severity and the consequence and the likelihood of that stuff happening. Relief Systems design is really focused on pressure excursions, while PHAs look at kind of any sort of excursion that could lead to a hazard. Moving on into the next section, minding the gap. This is all about constraints and nuances when using relief devices to mitigate risk. And I've got some anecdotes to share. But before we get to the anecdotes, real quick on the constraints in using a PRD as a safeguard. So one of the things that may come up in a PHA is looking at safeguards, like how can we get out of a certain scenario, or what is available for us to use as a safeguard against a certain scenario. And inside of a LOPA, if your company goes into LOPA, using a PRD as an IPL, an independent protective layer. So there are some pretty obvious constraints, and these are picked up by any good PHA team, is to say, well, to get out of this scenario, we need the PSV. So the obvious constraint is just to make sure it's there. Does it exist? The second, kind of moving on down the line in this continuum, is looking at the size of the device, looking at the discharge location, whether or not it can be isolated. And then it gets into more nuanced territory where the PHA team doesn't necessarily have this information, doesn't necessarily have the expertise to identify some other kind of nuanced constraints. And that's where a relief systems engineer can come in really handy. When a PRD is being used as a safeguard, it's important to consider how it's going to be used and whether it's appropriate. Obviously, it needs to be sized appropriately. Is it big enough for a given scenario? But back to some of the nuances, where does that PSV discharge to? Does it go to atmosphere? Does it go to flare? Does it go elsewhere? For a given scenario, is that scenario okay with the installed PSV trim? Is the PSV designed for vapor service, but you're trying to use it for liquid service? All things important to consider. Moving into my first example, let's say that we've got a PHA, a LOPA that reveals that there's an IPL gap. We don't have enough IPLs to satisfy our risk or to mitigate a risk. And so what happens, or what could happen, is that the PHA team assigns an additional PSV set at a similar set pressure to satisfy that IPL gap. So to paint kind of a picture of what this situation might look like, let's say that you've got a pressure vessel in some sort of service, and it's got two PSVs, and they both share common inlet piping. One of the PSVs is a spare, and the other PSV is in service. And so that whenever, during normal operations, let's say one of the PSVs needs to be taken out for maintenance, basically you use a big selector valve, switch it over to the spare, take the other PSV out, do some maintenance on it, put it back, and the next time you need to do maintenance on the opposite PSV, you change your selector valve. What I've seen happen sometimes is that something will go through PHA, an IPL gap is identified, and it's very convenient to fill that IPL gap with the PSV that's normally spared. So, take it out of being spared, keep it open all the time. But the problem with this is that it can cause further problems down the road. So while it's a totally redundant PSV, it's not really necessary. And the problem that you could create is that if the PSV is set at the same pressure, at the same set pressure, or a very similar set pressure, is that when the PSV is needed, both of those PSVs may start to go off at the same time, and they can cause instability in each other. They can have excess inlet pressure drop, or turning on that spare may require you to change out your piping to get rid of the selector valve and change it to a regular block valve and then a T instead. So the problem here is that you've created more risk and spent a lot of money and resources to fill a LOPA gap, and it didn't necessarily save you anything, it just created more problems. And this could happen because the PHA team assigns the other PRD as an IPL, but doesn't necessarily think about valve instability. It doesn't. Oh my gosh, I realized that this is not forwarded there. I think this visual might help out a lot more. The PHA team has not necessarily noticed there may be valve instability when recommending that other PRD. And those types of problems can go unrecognized for years until somebody in the Relief Systems group takes a look at it and realizes that something is not good with this installation, ultimately leading to more time and money and resources to fix. Another example, a PHA, and this actually did happen, and I'm aware of a situation like this. It's an unfortunate situation, but I think it's a good example. There is a series of LPG storage bullets. You can imagine in a kind of a refinery setting, chemical plant setting, petrochemical plant setting, where you've got these LPG bullets. They look like big, long silver hot dogs, or maybe they're painted white, but they've got that shape, and they're typically full of propane or butane or some mixture. They could be intermediate products, they could be finished products, but either way, they sit out, maybe in a tank farm. And a PHA took a look at these and identified that there is a potential for a liquid overfill scenario. So there's an upstream, maybe a depropanizer, maybe a debutanizer, which operates a lot higher than the MAWP of these vessels, and maybe they could overfill, and maybe you'd have a release of LPG to atmosphere, either through a flange leak or through a PSV. The risk associated with LPG going to atmosphere in this situation was considered so severe that it was completely unacceptable, because if it did happen, it could cause a levy, essentially. A LOPA was performed, and it was determined that there was a very large LOPA gap that could not be satisfied, obviously, by the PSV that goes to atmosphere, and it couldn't be solved with instrumentation either. So in the course of the PHA, in the course of the design to fix this, an additional PSV could satisfactorily fill that IPL gap. And so what happened was that a second PSV was going to be installed, and it was implemented as cheaply as possible. It did not go through a group of Relief Systems experts. It kind of left the PHA group, went to a projects team, and then got handled by a projects team. And so the cheapest way to get this fixed was to install an additional PSV and then route it to flare. And the flare that was used, because this was out in the middle of a tank farm, there's not a flare stack nearby, nor is there a flare header nearby. And so the cheapest way to do it was to install a flare subheader on the ground at grade. So while it for the PHA, it did fill this, it did close the PHA action item, but there were some unintended results. One, a grade level flare subheader that was full of pockets. And it's kind of obvious, like if you're from a Relief Systems background, if you've got a flare subheader that's full of pockets, there's a potential of having liquid in there. And if there's liquid in there, then you could cause all kinds of back pressure problems. You could reduce the capacity of the PSV you really want to be operating to help you out. And then the other kind of weird problem, and it was specific to this facility was that the other PSV, the one that went to atmosphere, the only residual scenarios that were planned for the one that still went to atmosphere was fire. However, many of the PSVs on this series of bullets continued to discharge to atmosphere sporadically in the absence of fire, which was really strange. Eventually, Relief Systems experts did catch this design flaw and kind of brought it up in the next round of PHA. And it was determined that the PSV that was installed to go into the grade level flare subheader was not as protective as it was intended to be. And the design fix was to essentially elevate the flare subheader above grade so that it could remove all of the pockets on its way to the larger flare header and then eventually to the flare. And so there were several lessons kind of learned the hard way, and this took many years to resolve. But the first was that the PHA team should have involved Relief Systems experts. The design, once it got handed off from PHA to a design group, that design group should have also involved Relief Systems experts. Installing the additional PSV to the flare header and the flare subheader was pretty expensive. Demolishing it was expensive. And installing an appropriate design was really, really expensive. So there was a lot of wasted opportunity and wasted cost associated with a bad design. Moving on to some case studies. The first case study I want to share with you is about T2. T2 is a specialty chemical manufacturer located in Florida that primarily made gasoline additives. Unfortunately, there was an accident there. There was an explosion because of a runaway reaction, and it killed some folks and injured a lot more, totally destroyed the business. The Chemical Safety Board investigated it, and some of the key issues that they found were related to hazard identification and chemical reactive hazards. On December 19, 2007, a reactor was experiencing a runaway reaction because it lost cooling. The reaction could not be controlled, and the reactor exploded. The owners were both chemical engineers, but they did not possess a process safety management mindset. They didn't think like Relief Systems engineers, and they didn't think like PHA facilitators or like a PHA team. They did not know the extent of reactive hazards in their process, and the facility did have a Relief Systems design basis and did have Relief Systems installed, but they were wholly inadequate. The process, and this really began because of how the process was scaled up. It went from a bench scale, maybe like a 1 liter reactor to kind of prove the concept, scaled up to a production size reactor, and the throughput was increased thereafter, but never did they perform a PHA or a Relief Systems design review. Doing either a PHA or a Relief Systems design review could have triggered one or the other to catch the potential reactive hazards and to possibly safeguard against the scenario ever occurring, or if it did occur, to have an appropriately sized relief system. Another case study is related to a more recent incident, the Williams-Geismar Olefins incident in Geismar, Louisiana, where there was basically another accident, an explosion, and a fire. And the CSB also investigated this and found that there were multiple issues, including overpressure protection, process hazard analysis, and then a number of other failures related to process safety management. Kind of the story on Williams Geismar plant's explosion was kind of a comedy of errors starting in 2001. In 2001, so basically, let me go back and paint the picture of how this process kind of operated. There's a propylene fractionator that had 2 reboilers on the bottom, reboiler A and reboiler B. For the way that they were operating it, it wasn't necessary that both reboiler A and reboiler B be operating at the same time, and so the idea was to have either one as a spare, so that once one of them fouled up, you could shut it in, put the other one in service, and keep on operating while you're busy, while you're cleaning the reboiler that's been fouled up. So in 2001, there was an MOC initiated to install some isolation valves around both of the reboilers. However, as part of like getting this started up in the PSSR, there was no identification of how to protect the reboiler, which was blocked in. That question was left entirely blank. In 2001, same year, there was a PHA, and it did not identify an overpressure scenario for the reboiler that was blocked in. It didn't recognize the scenario at all. The 2006 PHA, 5 years later, though, did identify that there was a potential for overpressure on the blocked-in heat exchanger and created an action item to lock open both of the valves, both of the isolation valves on either of those reboilers, such that those reboilers could take credit for a PSV. Many years later, that action item was closed, but it was closed in error. And so the way that the the way that the PHA action item was implemented was that they definitely locked open the block valve on the reboiler that was in operation, but they did not lock open the block valve that was on the reboiler that was not in operation. So the implementation missed the point of the PHA action item. 5 years later, from the previous PHA in 2006, it did identify the same exact scenario. However, they looked at the PHA action items and saw that it was closed, but without further inspection did not realize that it was not closed as intended. And then in June 2013, the standby reboiler was put into service kind of in an inappropriate sequence of events. Hot fluid was introduced to the hot side of the heat exchanger while the other side was still blocked in, which caused an overpressure and led to a BLEVE because there was no PSV available. Moving into our final section, boosting relief systems and PHA collaboration. So question, when do we work together? Inside of a PHA, PHA environment, relief systems engineers, if they're available to a PHA, they tend to be able to identify causes, consequences, and PRD safeguards pretty readily, maybe better so than some of the other folks that are in that meeting. Relief systems engineers often can take the call for PHA action items related to PRDs, and then relief systems engineers can, if they're involved, help prevent the misuse of any still-rated safeguards and PSVs to satisfy a LOPA gap if they're not appropriate. In relief system design, it's not very frequent that a relief systems team will call on a PHA team, given the frequency that the PHA teams meet. And even then, relief systems design engineers may only occasionally reference the PHA, and that's kind of a mistake on relief systems engineers' part. It does tend to be a one-way street. The PHA team typically goes out and is very proactive about going out to different parties and getting answers for them, whereas the relief systems team is usually hunkered down with a bunch of documents and doesn't really reach out to outsiders for help. Other areas in process safety management where there's kind of some overlap and where we work together, let's assume that for mechanical integrity during pressure relief device maintenance, mechanical integrity folks will review relief system scenarios, and they may also take a look at the PHA to understand risks associated with the process and the safeguards that are associated with that risk. For instance, if a PRD is being used as a certain safeguard, that may help them make a decision on when to do the PRD maintenance or to do the PRD maintenance at all except for a turnaround. In MOCs, MOCs can trigger relief systems design review, and they can also trigger a PHA review as well. The way things could have turned out for Geismar is a lot different. I think if folks had been working better together instead of treating PSM as kind of a checklist of things that they just have to do, if it had been integrated into the safety culture, it could have been a lot better. So for instance, the very first thing in 2001, as they were MOCing and getting these isolation valves installed, instead of leaving the answer blank on the PSSR about isolation from the PSV, if there had been some investigation, some thoroughness, it would have been possible to identify that there was a problem with the design, maybe have stopped or caused somebody to take a second look and determine that maybe those isolation block valves should not be all the way closed, and that maybe an open path to a relief device would have been necessary. Same year in 2001, the PHA team should have reviewed the relief system design basis for the propylene fractionator to understand what it was designed to do, checked the assumptions, checked any special considerations, and then possibly checked with a relief systems designer for new hazards identified with installing those block valves. It's quite possible they would have spotted it then. Collaboration between PHA teams and relief systems teams could have identified the problem a lot earlier and enabled them to come up with a viable solution a decade before the incident occurred. I do believe that there are better ways to work together for PHA teams to work better with relief systems engineers and vice versa. The first is to understand that there shouldn't be a turf war. Everybody in a PHA team, and even outside of a PHA team, it's important to recognize the different roles and perspectives that different folks have. It's not about who knows more or who knows better. It is about collaboration. It's realizing that it's not about you. It's about the process. It's about process safety management. Another good one is if you're confused, stop and verify. If you're working on a PHA team and there's a question about a pressure relief device, if you're not certain what it's there for or how it's designed, consider calling up an expert. Maybe there's a person in your plant. Maybe there's somebody that's in the corporate office that can help you out. Don't make assumptions if you're not sure. Consider handoffs. When an action item from a PHA gets handed off from one person to the next person, it's important for that person handing it off to ensure that the new owner kind of understands what's going on with this. If it's related to relief systems, and there's a lot of nuances associated with that, make sure that they're aware of the nuances before just passing it off and leaving it out there. The next is to get people in the room together. That's kind of the idea behind a PHA team, is that it's a composite of multiple different backgrounds, that there's multiple people with different kinds of experience and different kinds of expertise that you can get into the same room. However, that's not always how PHAs happen. Sometimes we've seen PHAs that are performed by 2 people instead of 4 or 5 or 6. And the way around those is that, sometimes that team of 2 will send emails and memos. Those take a long time to get answers. You don't get the answers you need to in time, and it leads to kind of maybe a sloppy job in a PHA. It's better to get people face to face. If you are on the PHA side of things, if you're a facilitator, consider identifying and obtaining permission to contact a relief system specialist over the course of your PHA. Having that on-call expert, that way you don't resort to sending emails or memos or turning things into PHA action items that somebody down the road is going to have to satisfy. Big key points from this presentation. 1, identify and understand the overlaps between relief systems and PHA. Understand that the goals of both PHA and relief systems are different, but in the end, they are both really for the purpose of mitigating hazards or eliminating hazards. Understand that PHA and relief systems, they may take different paths entirely to get to mitigating risk, but the paths do cross each other often enough that it makes sense for us to work together. Second key point to take away is that you should be aware of constraints, both obvious constraints and the nuanced constraints, especially when using relief devices to mitigate a risk. Understanding the constraints, especially the nuanced ones, can help save time, money, and possibly lives. And then the burden of better collaboration between teams falls on PHA teams, but Relief Systems have a duty to ensure that they're available for consultation. That does conclude the majority of today's presentation. I do want to move into questions and answers. So both myself and Tony Powell are both available to answer questions related to Relief Systems, PHA, and how they might overlap.
All right, thanks so much for your presentation, Justin. So as mentioned by, Justin, joining us for the Q&A today is Tony Powell. His expertise focuses on leading and managing hazard evaluations. In his career so far, he has completed hundreds of evaluations, both in the States and internationally. Annually, he facilitates 20 to 30 PHAs and oversees approximately 100 PHAs for clients of Provenance Consulting. We're glad to have Tony here to field any PHA-specific questions, so let's begin. I noticed that you have heavy emphasis on having a relief system engineer in a PHA team. Are you inferring that others on the PHA team are unable to determine if a safety valve should be used as an IPL?
That is, I'll answer that one. That is not the intention that Relief Systems experts are the only people that can determine whether or not a PRD can be used as an IPL. You don't necessarily have to do nothing but Relief Systems to understand that. I think the point that I'm trying to make is that folks that work in Relief Systems who are experts at Relief Systems can do a very quick and effective and efficient job of determining whether or not those IPLs are adequate or whether or not a PRD can be used as an IPL the way that the PHA team wants to, not that others in the room are not capable of doing that.
All right, thank you for that clarification. So for a plant which is upgraded in capacity to process higher feedstock, do we need to perform PHA for Relief Systems in the plant?
Before I answer that one, I do notice that Tony is on mute. I don't know if that's something, Armani, that you have to turn off, but I'll take a stab at answering it first. To re-ask the question, it's if we're increasing our throughput, does there have to be a PHA performed for the Relief Systems design? Was that the question, Armani?
Yes. Would you like me to repeat it, the whole?
Yeah, if you could.
A plant which is upgraded in capacity to process higher feedstock, do we need to perform PHA for Relief? Yeah, for Relief Systems.
So with respect to Relief Systems design, you definitely need to take your Relief Systems design to ensure that it can handle a new throughput. But Tony, are you aware of whether or not we have to perform a PHA for the Relief Systems if we're increasing our feedstock?
Yeah, so I don't know if the question was intentionally worded that way, but let me just answer, when you increase feedstock, do you have to do a PHA? And I would say that answer, it kind of depends. And what I mean by that is if you're increasing your feed rates, absolutely you have to look at the Relief Systems design and ensure that it's capable of handling that increased rate. Whether a PHA is required, I think you do have to review any hazards associated with that change and the level of PHA hazard evaluation, whether that's a PHA, whether it's a LOPA. Kind of depends on what's involved in the change. Are you installing new equipment to hit those rates? How much new equipment? What's the complexity? And as it gets more equipment, more complex, absolutely you need to do a PHA. If it's on the low end, it's not new equipment, you're just ramping up existing equipment that has had a PHA. Can you do that with kind of an MOC hazard evaluation? Probably. So it kind of depends on the amount of change and where you fall on the spectrum as to what level of hazard evaluation is necessary.
All right, thank you. Justin, when you were doing the LPG example, why did the atmospheric PSV need to be routed to flare? Was there a concern of atmospheric release, or was that atmospheric valve only used for fire?
So I'll answer in reverse order. I would want to say that the PSV was only sized for fire. That was the only thing that was ever identified for it. The big concern was that these are in LPG service, so liquid propane, liquid butane, which at atmospheric conditions, outside pressure and outside temperature, tend to vaporize. However, in an overfill scenario, which was the hazard identified in the PHA, there's a potential that the liquid level on these propane butane bullets could get up to the very tip top of the vessel, could reach an overpressure situation where the PSV is now opening, and then start spewing, flashing liquid and vapor LPGs to atmosphere. It's not as if it's all going to vaporize in a nice cloud and go away. There's a strong potential for a lot of it to remain liquid, splash down on the ground, create a pool that could catch on fire or explode. So that was the reason you could not get away with using the atmospheric PSV, was specifically because of the liquid discharge of LPG to atmosphere.
All right, thank you. So following that, what would your suggestion be for the liquid situation? In
this situation, there was not a viable way to prevent the liquid overfill with instrumentation. It would have caused more problems to have installed, for instance, automatic isolation valves that would meet the spill requirements to fill in that same LOPA gap. I think the best way to handle it would be to use a PSV discharging to an enclosed system like a flare, which was kind of the idea, but the first implementation was not good because it went to ground instead. It went to a grade level flare header.
All right, thank you. I have another question about PRDs. If I have a PRD designed for a gas blow-by case or blocked outlet, could I give it a credit in an external fire case?
When we say credit, so for credit, I'm not sure, and credit for a fire case is also kind of a curveball for PHA, so let me answer it in pieces. If you've got a PSV that's sized for gas blow-by tend to be, well, it depends on the situation. They tend to be kind of severe scenarios. As long as that PSV is adequately sized also for the fire, yeah, of course, you could use the same PSV for the fire case. My assumption would be that the original Relief System design basis would include not only gas blow-by, but also the fire case if it applied. Now, when we talk about credit has a certain ring to it that we don't necessarily use in a Relief Systems design, so I don't know if the person asking the question is meaning can we take credit for it as an IPL for the fire case. And with a fire case, Tony, you can back me up on this, the fire case is not often a scenario of concern in PHAs, but I have seen them before. So my question for you, Tony, is have you ever run into a PHA that had a fire case that had to go to a LOPA where IPL credit had to be determined?
So I don't believe so, not a LOPA scenario. One of the big qualifiers for LOPA is you've got to have a single discrete initiating cause. External fire, just kind of arbitrarily, external fire doesn't generally fall into that. So it's not something you would typically LOPA. But it was just if you did, the answer is yes, as long as the PSV is adequately sized to mitigate the hazard that you're talking about, then it could absolutely be taken as a credit.
Yeah, so we kind of go right back to the PHA team reviewing the Relief Systems design basis to determine if a PSV also identified the scenario and if it's sized for it.
Yep, that's right. It's not a typical LOPA scenario though.
Gotcha.
All right, thank you. So there's another question following that LPG example. So why was the higher set pressure valve sporadically opening when it was set at 270 psig, and the lower set pressure PSV is set at 225 psig?
I wish I knew the answer to that question, but there was never, for any of the times that it did it, it probably did it about 5 times over the course of 5 years. Not the same PSV, but multiple PSVs in a couple of different batteries that got piped up this way. There was never an investigation to determine why those PSVs would go off. I would love to know. I don't know the reason why. But it certainly kind of scared people that if those PSVs could go off in the absence of fire, could they also go off if there was a liquid overfill scenario before the other PSV went off? So it did, even though there was not an incident investigation for any of them, it did kind of create some more impetus to change the design.
All right, thank you. And I have another one here. What would you advise to do if PSVs that are identified as safeguards are not properly documented in the Relief Systems design basis? For example, if the Relief System says overpressure doesn't apply.
I think that would trigger. It would definitely trigger another review of the Relief Systems design basis to understand what the PHA is seeing that the Relief System design basis does not see. I think it really depends on the situation. And it could be because the PHA is qualitative in nature. Maybe it sees that there's a potential for an overpressure that the Relief System does not see, and it could be the case that the Relief System design basis did cover it. But found that the true, maximum upstream pressure of the protected system was not enough to cause a relief scenario. It could be just because of missing documentation. And what I mean by that is maybe a non-applicable scenario did not get rationalized, and so it looks like it's missing, or it looks like it was missed when a PHA team goes to review it to see whether or not the scenario was covered. So it could just be a documentation gap.
All right, thank you. I have another one. Can we incorporate cybersecurity while doing PHA for relief systems? And would it be helpful in case linkage is lost between DCS and PSV?
So I'll let Tony chime in with his opinions on cybersecurity mixed into PHAs, and then I guess also mixed in with relief systems. In my experience, there's very little, if any, instrumentation, say electronic instrumentation, connected to the pressure relief system. Most of these devices, by far, are all mechanical in nature. They don't require some electrical signal to activate or anything else. And the only sort of instrumentation or sort of electronics that are associated with them might be a pressure indicator, a flow indicator, maybe a tattletale located on a rupture disk to tell operators that the disk has been burst, and not necessarily anything related to the actual function of a PSV when it needs to function. Tony, have you got any experience you want to share with cybersecurity in how it relates to PHA, and then also in how it relates to pressure relief systems?
I really don't have anything to add on that, Justin.
All right. Well, I hope that the person asking that question got a satisfactory answer, but if not, shoot us another question.
All right. And so earlier you just mentioned about rupture disks, and one of our attendees asked about it. Do rupture disks cover all overpressure scenarios?
The answer to that question is they can, but it depends. It depends on whether or not that rupture disk has been designed for a given scenario. You could have cases where you've got rupture disks in line with PSVs. Those are called like combination devices, or you could have a situation where you've got rupture discs in parallel with PSVs. Maybe the PSVs are installed there for kind of just general lower level process upsets, whereas the rupture discs are sized perhaps a lot larger, and they are there for something very serious. An example might be a runaway reaction, where the required relief device sizing may be much, much, much greater than what the PSV can handle, and it just makes more sense economically or in practice to install smaller PSVs and then one big large rupture disc to handle something else. But the answer to the question is, it depends.
Okay, so you talked about having the rupture disc and the PSV in either parallel or a series. Is there like a pros and cons to this, to like each side?
So sure, as with anything else. So there's all sorts of little nuances, but it just depends on what your facility needs, what your process needs. Some use cases where you may have these combination devices. Say you've got an inlet rupture disc just upstream of your PSV. You may need to use that because you want to ensure that there's no process leakage out of the PSV. You want to make sure that if you've got something like butadiene, butadiene is a good example. Butadiene on contact with air tends to form a polymer. So you can imagine that if you just had a regular PSV connected to your butadiene storage, and if there's any sort of leakage out of the PSV, you might not detect it. Over time, you might get a tailpipe full of popcorn polymer. And so when the PSV is really needed, it opens up, but you can't relieve because your tailpipe is totally blocked in with polymer. In this case, it makes sense to isolate upstream with a rupture disc so that there's no leakage to the PSV. The drawbacks of a situation like this where you have to have a combination device is that maybe your maintenance needs are increased. Maybe you've got to more frequently go out and change your rupture disc. Maybe you're prone to accidental rupture of your rupture disc. Maybe it buckles and breaks a little bit too frequently. On the other side, if you've got parallel devices, let's say you've got a PSV on one side of your vessel and then you've got rupture discs on the other side of the vessel, and both are intended to protect against different scenarios. Again, it really depends on what you need for your design, but you can create some nuisance situations similar to the other example. Maybe you've got to do more frequent rupture disc replacement on the rupture disc that's on one side of the vessel. It really just depends on the situation.
All right, thank you. And I think this will be the last question we have here. So one of our attendees recalled a day passed when PSVs were the last line of defense and positively protected the system, regardless of a PHA or LOPA score, and mitigated the scenario. Is this mindset supported any longer, where if the system has a PSV, no further consideration is required?
I can totally get down with that mindset as a kind of a relief systems engineer, somebody that has that relief systems mindset. If I've got a PSV and it's adequately sized for whatever my scenario is, I'm happy. I'm satisfied as well. I don't care what the LOPA says. I don't care how many IPL credits I can get for it. My PSV is good. I don't know, and Tony can chime in on this one. I don't know if the same mindset exists within PHA teams or within other groups who have an interest in risk management or process safety management. So, Tony, I'll kick it over to you. If I think a PSV is good, why is that not enough to satisfy the PHA?
Yeah, and this mindset really did exist in years past. As more companies and people are adopting kind of the LOPA methodology, that's really where you run into a real problem. So you essentially are getting credits for all the protections that you have. They all have some level of credit, but you also, in a PHA, have to realize that really everything, including PSVs, have a probability of failure on demand. So just because a system pressures up, a PSV, it will fail on some frequency. Maybe that's once in 10 years, maybe that's once in 100 years. Somebody might claim it's once in 1,000, but still, there is a probability that will fail. That's where LOPA comes in, and you get certain credits to reduce your likelihood, depending on what the IPL is. So you do certainly get a credit for PSVs, but oftentimes it's not enough. If the consequences is on the very high end of severity, it's going to require more than a single PSV, in some cases more than 2 PSVs, because they have a probability of failure. And a lot of times for LOPA, the frequency that we're targeting for the higher severity consequences are extremely, extremely low. I mean, once in 1,000, once in 10,000 years. So more than a PSV is typically required for high severity scenarios to get to the levels of likelihood that the LOPA is requiring.
Yeah, I know, Armani, we've only got like 2 minutes left before we have to close this up, but I think what Tony said is really, it highlights the whole reason for today's webinar. I want PHA teams and Relief Systems engineers and everybody else on the call to recognize that in a situation where you use LOPA or something similar to start, creating additional IPLs, or you need to fill these gaps, is to get a Relief Systems person in there to help steer away from inadvertently bad designs that are only intended to fill a LOPA gap.
All right, thank you so much. I believe that'll be the end of our Q&A session. One moment. If you have any additional questions, please contact Justin Phillips at the email provided here.